Hello everyone, welcome to a new tutorial. Today is going to be relatively easier, so we are going to go a bit slower, and what we are going to cover today is the first publication where we use this side on real observations. So I hope that you will find it interesting, and also I think it serves as an update to just show you that in principle the code is ready to be used. It's just that sometimes it takes time to get results and to publish them, but I hope you will like today's tutorial. Okay, so then let's start just making myself a bit smaller, something like this. And the idea is that I think it's better to just go through the paper instead of preparing like a formal presentation. So the idea is that the paper is already accepted, and now it's basically going to appear very soon in Astronomy and Astrophysics, and now it's available in archive. So I wanted to just briefly summarize what we did, what things we believe it work and things work, and also what things that we believe in principle they are working, but there are some results that we still are not sure about whether they are correct or we need to play a bit with the configuration. So I think it's going to be like a relaxed chat about the results. So then what we have is that the first author and the leading person doing this work is Fabiana from the University of Catania, and then I help with everything that I could. So I would like to present you today the results. It's a very interesting work in the sense that we are going to embed, we're going to perform inversions of full Stokes vector of an iron 1 transition, so 6173, and a calcium 2 transition in the infrared, 8542. And calcium 8542 will be non-LTE, treated non-LTE. And the interesting thing is that I don't know exactly why, but we started testing the code with real observations that I think they are probably the most challenging one that we can use, that is an observation of an X-class flare. Okay, but I think it's a good starting point in the sense that we can check how the code behaves in such really difficult condition. So I will just recommend you to read the introduction if you want to have some context. The important thing is that we are using data from IBIS, then it means that we have an imaging instrument. So it means that we record this spatial information, the 2D information for a single wavelength point. Then we tune to a different wavelength point, and then we record again the 2D information. And this is done for one spectral line, and then another spectral line is tuned after that. So then in principle, we don't have strictly simultaneous observation of the two lines, but they are separated for just a few seconds. I think the final cadence from complete one transition and the other one was around 30 seconds. So in general, I think this is a good cadence. For an X-class flare, it's maybe in the limit, but as it is what we have, we believe and we treat it as they were treated, observed simultaneously. But just be aware of that. So imaging instruments, the 2D information is instantaneous, but the spectral information is taken at different times. And then if you add different spectral lines, then there's a delay between one line and the other. Okay, so besides that, we do the normal thing. So we check that the spectral lines, they have a uniformly sampled spectral wavelength, and if not, we do the interpolation as we have done in previous tutorials, and then we add negative weight that will prevent the code to use the interpolated values, the new ones during the inversion, but just to keep a uniformly sampled spectral wavelength. Then we also need to normalize to the local continuum. In the case of the iron line, that was easy because we observed the continuum. In the case of the calcium line, that was a bit tricky because in general, filter graph instruments, when the line is very broad, they don't usually reach continuum. So then what we did was we did a synthesis using the HSRA as atmosphere, so the Hadvar-Smithsonian atmosphere. That is the one that is used internally for normalizing the continuum intensity, so the local continuum with the side. And we did the synthesis of the calcium line using that reference atmosphere at the specific heliocentric angle. In this case is 0.9, it's almost the same, but still we wanted to do it as correct as possible. So then we had the full synthetic profile from calcium, and then we use that to compute the intensity ratio between the continuum and the farthest wavelength point that we observe with IBIS. And with this we obtain a scaling ratio, and then we use the normalized and average normalized continuum intensity from a quiescent region that had a continuum level of 1, but it was not the continuum, so it's just the farthest wavelength point was normalized to 1, and then we rescale it with this scaling factor from the synthetic profile. If you want that I made a tutorial about this, I can make it, so just let me know. But if not, I think it's explained in the paper, but if not, I can explain it later on. But with that, we had the continuum normalization and then the wavelength grid, and then we prepare the profiles to run the inversions. As always, we of course we use this side, and then we started the inversion with a set of initial atmospheres, the ones that are in the tutorials. I think they are 12, and they go from log tau 1 to minus 6.8, if I'm not wrong. And then with that, we started the inversions. So what did we embed? So this is a reference image from SDO. This is an active region that produces an X-class flare in 2014. And the idea is that the IBIS field of view is the one enclosed by the blue rectangle. So then here we have the activity. And if we take a look, for example, at the information, the spectral information from the iron line and the calcium line, we will see that we have like a sunspot here and then some activity here. This is continuum close to the iron line. Then the line core seems to be similar, and then we have some linear polarization and circular polarization signals in different areas. So from the sunspot penumbra, but also here there are some signals. But the important thing is when we look at the calcium line. So in the farthest wavelength point, that remember is not the continuum, is closer to the line core. We have this distribution, probably similar or even a bit higher than the line core of the iron line. But then when we go to the line core of calcium line is where things get interesting, because we still have the shape of the umbra, penumbra in this area, but we have a very bright region here. So you see white color above black, but also check the level. So this is local continuum intensity, and we have 2.5 values. So in those regions, the line core of the calcium line is extremely enhanced and is in emission. I will show you profiles later. So then the idea is that in the regions where the flare is happening, there's extreme heating and is producing a very complicated Stokes profile for the calcium line that in fact is extremely enhanced and is in emission. Linear polarization signals for calcium are difficult for us to understand. It seems that they are very weak or they are below the noise. So in fact, I will show you later the configuration that we use, but we believe that we don't get too much information from them, at least for the calcium line. And then in the case of the circular polarization signals, we have reasonable signals and strong signals in the regions where the flare ribbon is actually located. In this case, we will see later, and maybe we will discuss it, are those signals due to really strong magnetic fields or due to the enhancement on Stokes that also produces an enhanced Stokes signals? I think probably a combination of both, but it's something that we will discuss later when we analyze the inversions. So then we started the inversion. We did a lot of tests because it's not only the first time that we tried on data, really going through all the process and checking the details of the results, but also it's the first time that we tackle an X-class flare. In fact, I think I've never done inversions of a flare. So then we started with a lot of tests and until we got reasonable configuration. So we are going to run it 4 cycles, and then this is the well, I can show you. So I will share in Dropbox the configuration files that we use in the inversion, so in case you want to check it. So in the case of the control file is this one. So we are going to run 4 cycles, and then the weights I will comment it later, but just let's start with the nodes. So we reach 6 for temperature, and then microturbulence we add 2 at some point, and then we have parabolic behavior for magnetic field and inclination, and then we go a bit higher for velocity because we expect that velocities are going to be some of the characteristic features of the flare. And then for azimuth, as we said, our linear polarization signals mainly for calcium are really low, so we didn't want to go too much. And also we didn't have a spectral profile PSF, so then we just left the microturbulence as free parameter to allow to enhance a bit the synthetic profile and match the observed one. In the case of the weights, as I mentioned, linear polarization seems to be too weak to maybe extract too much information from it, so we just decided to put more emphasis on Stokes V. And then Stokes I, we wanted to have it well fitted because, as we said, they are really complex, and we believe most of the thermal information should come from Stokes I. And then we just put 1 to Stokes Q and U, mainly because in the photosphere we have more signals, so it's also important to get good fits on Q and U. And I think this is the main element from the inversion. I think this is something that we have also tested during the previous tutorials. But I think the interesting thing is that we did inversions. So this is another figure. I think you can check this one. I think this tutorial or this video is more focused on the inversion itself. So then the idea is that we did a lot of tests with the configuration I show you, and also with the 12 initial atmospheres. And the idea is that at some point we started to get good fits, and the way we evaluated those fits, it was through the Python wrapper. As you remember, we can put a threshold for the chi-square values, I think here. So we can put a threshold for the chi-square values, and also we set the number of initial atmospheres. So at some point we were seeing that the 12 atmosphere were fitting well. We can see that the chi-square value that we get from the wrapper is an inverse one. So a value of 1 is perfect, almost perfect fit, at least in between the noise level, yes, in between the noise level. And then if you get 0, it's really bad. So then we were looking for having a smooth distribution of colors. In this case is almost 1 color corresponds to 0.1. And we saw that the ribbon was well fitted, but at some point we started to see that even if we change the configuration, the fits weren't extremely good, but in some cases yes, but not for all the pixels. So then we did an additional change for these inversions, and now you can see that instead of 12 I have 21 here. So then what we did was to pick different pixels from different areas of the field of view where the fits were really good. And sometimes you had really good fits and then maybe pixels surrounding it not so good. So we just picked those pixels and took the atmospheres and used them as initial models. We know that this is not what I usually recommend, because I always recommend to start from standard flat atmospheres for magnetic field, velocity, and inclination, azimuth, etc. But in this case, we knew that the code was getting sometimes the good fits, but sometimes it was not able to obtain them. So then what we did was to add all these atmospheres, but in order to prevent to go directly to a solution close to those atmospheres, where we maintained or we kept the 12 initial atmospheres, and then after that we added the atmospheres that we selected from different pixels. So then for a standard case where the code was getting good fits, it was probably going to use the first 12 atmospheres. And then for pixels that in principle the profiles were not so different and those where we got good fits, maybe the code need to try different atmospheres, maybe some of them that were also obtained by the code in the previous test. So then we had a combination of initial atmospheres from standard, HSRA, FAL-C, FAL-F, and then from previous inversions. But these ones, they are only examined or used after using the other 12. So we believe it's a good middle ground in the sense that we were getting really, really good fits. So you can see that white, it's almost 1. So usually we got like 0.95, 0.96 in all the area containing the flare ribbon, and also in areas here and here. So we were extremely happy with this configuration because we were removing this salt and pepper pattern that you usually get when you start inversions pixel by pixel. So we were extremely happy, and the truth is that as we were focusing this work on the study of the flare ribbon, we just stay with it. But it's true that if you check this area, that is the area containing the sunspot, fits in general are not so good, and we tried different configurations and different weights, but we didn't really get them working perfectly without degrading the fits of the flare. So probably, so in this case we just left it like this because we were focusing on the flare ribbon, but probably in the future, if someone wants to get really good fits in all the areas, I think probably you need 2 configurations. So you need to break the field of view in 2 and invert them with different configurations. And this, although it doesn't seem very easy to do, or at least a bit cumbersome, it's not so crazy in the sense that you have one area where a flare is happening and you have extreme heating, and then you have an area where it's like a sunspot where you have very cool material. So even if the code should handle everything properly, if you happen to have these discrepancies, I think it's better to just put one configuration for the sunspot and one configuration for the flare itself, for the flare ribbon, and I think this will simplify the time required for testing and finding a perfect configuration for both. So I think this is something that we will try in the future, but if you face this problem, just divide the areas of interest. If they are so different like this, well, in this case, just divide them with different inversion configurations. Okay, so then we did a lot of tests. We saw that the code was fitting well the profiles, and we were happy with the configuration. So then we moved to check profiles and present them, and also to show how good the fits are in general. So this is one of the best pixels that we found. We have that iron line is well fitted in general, almost perfectly, I would say. And then you have calcium that, as I was mentioning before, it's really a strange calcium profile because it's really hot due to the flare, and then the core is in emission, and in this case up to 1.5 for the continuing intensity. And the fit is very good, is the color line. And then also for Stokes B, I would say that is perfect. Again, for linear polarization, we are here a bit confused in the sense that the amplitude of the signals is not extremely low, but the shape of the signals, it looks like noise to us. So in these cases, we believe that even if we tune the weights to improve the fit of the linear polarization signals, I'm not sure how the code can change the atmosphere to produce this rapid behavior for the Stokes QU signals. So at the end, we were not sure exactly if this is a signal that is so complex that we don't understand, or if it's that the noise level it's too high to see actually the profile. Okay, so then we assume that good fits meant Stokes I and V in general, but not in the case of the iron line. In the iron line, we also wanted to have Q and U signals well fitted. So then if we move to next profile that we wanted to present, we presented 2. In this case, we wanted to present another profile where fits were not perfect, but still we were very happy with them. In that sense, again, here, Stokes I is completely complex to for the calcium line. You can see now it's 2, and the line core intensity is level 2, but still the fit is very good. Stokes V is also very good, and again Q and U, I think there's not much we can say in general. And then we see that sometimes the fits were not perfect for the iron line, so we wanted also to present an example where we were very happy with calcium, not so happy with iron, but in general we believe that still this is a good fit, mainly due to the complexity of the calcium intensity profile. So then we were happy with the fits, so then we started to analyze the atmospheric parameters. We picked 3 optical depth layers, so 0, -2, and -4. In general, we expect that calcium reaches higher in the atmosphere, like -5, -5.5. But in this case, and as we will show later, we found that the region producing the flare, the material is so hot that the height of formation of the calcium line will be affected by it, and in general it will drop. So then we believe that the height of formation of the line core of calcium line, mainly for the region corresponding to the flare, is closer to -4 than to -5. So then let's check just quickly. Temperature in the photosphere looks fine. -2 also looks down, some heating is appearing, but then at lockdown -4 we see a strong heating in a very concentrated lane. That is where the flare ribbon is located. We see a correlation with most of the parameters, but in particular velocity. We see strong velocities. Blue color means negative velocities, upflowing material. So then in the region where the flare is happening, the material is going up towards us. And then we see small concentration of magnetic field. It's not so different, but still it seems that if we check the contour where the temperature is really high, there's a bit of an enhancement of the magnetic field. And then we see a clear correlation with the magnetic field inclination. So in this case, the magnetic field is really vertical in these areas. And then we have this interesting pattern that is an opposite polarity and a smooth transition with an inclination of 90 in these white areas, that we see something in the temperature panels, but we see a strong correlation in the velocity panel. So where we have this magnetic field configuration that has an opposite polarity of the surrounding magnetic field, we have low velocities. And also something that we found interesting, and the truth is that we are not really sure about the reason for it, and we hope we will try to look at it in the next month with additional studies, is that it seems that there's a strong correlation between heating and low velocities, and we are not sure about why. We were expecting that the region with strong heating, that is the main responsible of the flare, probably was the reason the region also moving faster. So we checked the profiles, we tried to look at if there was a missing fit of the Stokes V signals or something like that, and there's no indication that the fits are wrong there. It doesn't mean that the atmospheres are correct, but it means that at least the fitted profiles are well fitted, at least in the range of fits that we show in the previous figures. So we are not really sure of why there's a strong correlation between these strong velocities and the absence, or at least velocities are much weaker there. So this is something that we want to study in the future. And we also did a cut of the atmospheres through all this entire region that is highlighted with dashed lines. It's interesting because it's cutting all these velocity patterns. It's also cutting the different inclination patches, and we show them here. So just at the beginning, let's focus on the background. Let's forget for now the line. And we have that again, temperature, it seems that here is what we expect in, let's say, quite sun areas, but then we have the strong heating in lower areas or lower layers in the region where we have the ribbon. And then it goes again to, let's say, more standard atmospheres, and then again an additional heating. This is accompanied by strong velocities, and again we see that in this region where the temperature is hottest, the velocities are in general much weaker, and then again we see the pattern where velocities get higher here. Magnetic field, as we said before, in general, looking at the contours, it seems like maybe some minor enhancement it's happening, but when you look at the cut, there's no clear correlation like when you look at the temperature or the velocity pattern. So we cannot really say that we see strong correlations with the happening or the event related to the flare and enhancement of magnetic field. And then again, inclination, we can see that it's really smooth. So we have one polarity, then we have this region with almost horizontal fields, then opposite polarity, then again opposite polarity, horizontal fields. So probably these structures, they were interacting, and maybe not the cause of the flare, or maybe yes, but at least there's some interaction between opposite polarities at this point. So I think it's something that we will study also later on with when we study additional snapshots from the observation. So then the final element that we wanted to include was that we were seeing just by intuition that log tau -4 panels for all the atmospheric parameters look much better and closer to the chromospheric information that we were expecting from the calcium line than log tau -5. So then in that sense, what we did was, okay, let's compute the response functions for the two lines, combine them together for the different optical depth and for all wavelengths, and for a quiescent pixel, or the closest that we have the quiescent in this observation, and for a flare pixel. So then what we are showing here is that in a pixel where it's the farthest that we can get from the flare, if we take the average, so the maximum response function from all the wavelengths and the two spectral lines and the 4 Stokes parameters, we get these equivalent lines that cover the range of optical depths that we use in the inversions. And we have the behavior that we were expecting with two distinct peaks, one from the photospheric line and the wings from the calcium line, then are relatively dropped in these layers, -3, -4, and then a peak again that is from the line core of the calcium line. And this, as we were expecting, this line core peak is close to -5, log tau -5. But then in the case of the flare, things collapse. So we still get these two peaks, but now the main peak for the probably from the calcium line, it's between -3 and -4. So then in that sense, what we are seeing is that the height of formation is getting squeezed. So then the line is not reaching as high, maybe because of not simply because of the flare. So then in this case, when analyzing the atmospheric parameters, we should be a bit conservative and try to not go to -5, because as you can see here, the response functions are completely dropped before that. So then we are not being sensitive to log tau -5 in the case of the flare. So then just be careful about that. If you have such an extreme event like this one, be careful when using so when studying the atmospheric parameters at different layers. You have to be sure that the atmospheric conditions are not changing the heights where you are sensitive to the atmosphere. And in that sense, we picked the maximum height corresponding to the calcium line, and you can see that in general the maximum sensitivity for the full Stokes vector from the calcium line, it's around -5 in the region outside the flare, and then it goes deep, and in fact where we have extreme heating, it's essentially -3, and then it goes back again, and this happens for all the atmospheric parameters. So just be careful about that when you're analyzing this type of events. And I think this is all more or less what I wanted to say today. Yeah, so essentially this is the first paper where we really went through all the process to perform inversions and analysis of the observations. It's a challenging project because the X-class flare profiles are really extreme, But for me, the one of the main conclusions is that the code seems to behave well. We could get good feeds, and the code was stable. Also, the inversion of the full map, because we went for the full map. So you can see here that this part here that you are seeing the chi-square values and the atmospheres, it's the complete field of view of the instrument. So we could that in, and I think the inversion time with the 21 atmospheres and the best configuration that we could get was around 5 days. So the code is behaving well and is still very fast, even when you are really pushing it to the limit with such a complex observation. So then in that sense, I think it's a good update. If someone is still interested in using the code, I think the code is ready to be used. Of course, I'm always available to try to help. Sometimes I don't have the time, but still I'm available, so just contact me. And I think we are very happy because this is also a starting of a collaboration with Fabiana, that we are going to now analyze the time series, because we focus on one snapshot because we were basically testing the code and also trying to get information. And now we are embedding the complete time series in different times slots to get also the evolution of the atmospheric parameters after the flare peak. That is the one that we have here. So I think that's all. I hope you like this tutorial and this paper, and also I hope that you would like to use this someday. So I think that's all for today. Thanks a lot and see you soon. Bye.